and we start our spring session. Actually, now we have New Year even in China, so let's start. We already have a schedule for the whole semester, and the first talk will be my, and let me demonstrate the screen. No, is it visible?
Yes.
Yes.
Okay. So the title of my talk is the following. This is isonormal processes associated with Brownian motion. Let us recall some initial definitions. First of all, consider H. This is a real separable Hilbert space with Norman product, and define a Gaussian family of random variables such that it is a linear with respect to argument from H, and has the following distribution for every H. Because of its linearity, the notation psi H, like for inner product, is used, but when H is infinitely dimensional, then psi cannot be associated with any random element in H. It is just a family of random variables with such properties. And we will say that psi is a Gaussian white noise in H. Now let us specify our Hilbert space H, which we will use. Let us suppose that phi, which acting from Rd to R, is positive definite continuous function, which is symmetric and such that phi from 0 is equal to 1. Then one can define the following inner product on the functions. Let us consider linear combinations of functions of the kind. We just move our function phi to the point uk, and then consider the sum with coefficients ak. Then if we define the product fu, phi u, phi v as phi u minus v, then it occurs that due to the condition that phi is positive definite, one can easily check that this is a real scalar product. And even more, since phi is strictly positive definite, then this is a scalar product, and then we can define reproducing kernel Hilbert space based on the function phi as a completion of the set of linear combinations with respect to this scalar product. And we will use the notation H phi. Okay. By the way, it is good to note that for good functions phi, which rapidly decrease at the infinity, this is not something abstract. This is a space which consists of functions, by the way. Now let us note that there exists a natural lifting from Rd to reproducing kernel. We just map the point u to the element I will denote it by phi capital from u. This is our function moved to u, and this is element of our reproducing space. It is natural to define such lifting, but it must be noted that this mapping is not linear. In fact, for every u, the norm phi u is equal to 1 because of the condition on our function phi small. So we have such a mapping which maps RD to the sphere, to the subset, of course, of sphere in the reproducing kernel space. Now let us consider Brownian motion. It will be a standard Brownian motion in RD. Then, due to continuity of the map phi capital, this phi capital from BT is a continuous random process in HV. Then let Xi be a Gaussian white noise in HV, which is independent from Brownian motion. The main object of our investigation in my talk is the following. A random process eta t, which is equal to Xi applying to the random element phi capital from BT, is called by isonormal process associated with the Brownian motion. Remark, let us see that the value Xi from BT can be easily defined when we use this orthonormal basis En in HV. By the way, due to continuity of phi, HV is separable, so it has orthonormal basis, and due to independence of B, then B phi capital from B and Xi, this sum does not depend on the choice of orthonormal basis. So our isonormal process is properly defined. The aim of the talk is to present the connections between the properties of eta and Brownian motion. Some simple considerations. For every t, the random variable eta t has a standard normal distribution, but the process eta is not Gaussian. So it just consists of Gaussian variables, but they are not jointly Gaussian. Let's see why it happened. Let us calculate characteristic function of the finite dimensional distribution for eta. The expectation of this exponent is equal to, I am taking initial expectation, conditional expectation, just fixing B Brownian motion. Then we will get the following expression, and we see all statements of the lemma. For example, if n is equal to 1, then the expression inside of the brackets under exponent just equal to -1/2 of lambda squared. So it doesn't depend on Brownian motion B, and we see that eta t has a normal distribution. From other side, if we have n bigger than 1, we see that we just integrate this form, this expression, this quadratic form in the exponent with respect to distribution of increments of Brownian motion. So we get a non-Gaussian answer. Okay. So next step, lemma. I will suppose now that phi satisfies some Hölder condition. In this lemma, it doesn't matter which is its which is the number corresponding to the Hölder condition. Then process eta has continuous modification. It's a rather simple calculation, but how we can proceed it? Note that the trajectories of Brownian motion are Hölder. Consequently, under fixed Brownian motion, process eta is Gaussian and Hölder and square mean. Here it has continuous modification. Now we just apply for BDC. Now let me recall you the connection between the continuity of white noise processes and geometric properties of the subsets in Hilbert space. Let us note that lemma, the trajectory of phi capital BT can be covered by the Hilbert-Schmidt brick erasure. Let me recall what is Hilbert-Schmidt brick. Hilbert-Schmidt brick is constructed with the help of orthonormal basis and sequence of numbers an such that the non-negative and series of squares converges. And
ask a question: is this brick is it the same for all omega or?
No. The brick depend on the omega.
Okay.
And the brick is just a set of such element of our Hilbert space that every coordinate is less or equal than an. How we can do this? Let me recall you the theorem which was proved by me in our joint paper with Mikhail Popov. And this theorem is following. If we have the set U in Hilbert space such that the random field where H elements of U are used as parameters of this field has continuous modifications, then it can be covered by Hilbert-Schmidt brick. And now let's check. Now the role of this compact set U is played by this set, where phi capital from the ball is just set of all phi from U, where U belongs to the ball. And ball, this B with B0R is just closed ball. Now let us take this ball, and we know that trajectory of Brownian motion for every omega is continuous function, so it can be is the image of the continuous function, so it can be put it into the ball. And what we just need to check that Xi has a continuous modification on this ball. And here the following must be noted. We have to be careful here. Because of in our theorem with Mikhail Popov, let me recall you, we just work with the natural distance between the element of this space H phi. Just before we said that it has continuous modification, but with respect to t. This is slightly different things. This is the reason why I am considering the ball, and in this compact set, U capital equal phi capital from B0R we can define two different distances. One is the distance which it inherits from RD. This is just distance between pre-images. And other one, it is natural distance. But this is a compact, and we have one-to-one continuous correspondence. So these distances are equivalent. And we already use Hölder arguments just to check continuity of isonormal process. So one can say that this one is continuous, and then we have everything which we need. So what we can say? We can say that trajectory of our phi capital from BT, is a compact. Of course, it is compact, but it is slim compact on our infinitely dimensional sphere. Okay, now let's come back to our process eta t. And it can be checked that eta t is strictly stationary. Let me recall you the characteristic function of the finite dimensional distributions of the process eta. You see that it is described via the integration with respect to the set of increments of a Brownian motion. But Brownian motion has stationary increments. So from this expression, we see that process eta is strictly stationary process. Also, let us see this expression much more carefully. Suppose here that function phi rapidly decreases to 0 at infinity. For example, suppose that phi has a form like exponent minus norm square of u, or something like this. Then we can say that process eta is not only strictly stationary, but we can say much more. We can say that it will satisfy a mixing condition, and it is evident why. Because when the distance between time arguments in this last line became to be big, then our Brownian motion, our increment of Brownian motion became to be widely distributed, and the integral with our function which decreases at infinity, decreases to 0 at infinity, became to be equal to 0. This is the idea why we can say that when function phi decreases to 0 at infinity, then the process eta satisfies mixing condition. So it is a good stationary ergodic process. Now let us try to investigate the local times of isonormal process. Start from the one-dimensional case. So now I suppose that process B, our Brownian motion, take its values in R2, and function phi has the following kind, where the number alpha belongs to the interval 0, 2. Then the process eta has a square integrable density of occupation measure. Let me recall that occupation measure is following, and to check the statement about the existence of the square integrable density, we can proceed via standard way. For example, it can be found in the articles of Rosen, that we just check integrability of its Fourier transform. Due to the definition of the occupation measure, we need to check such expectation. Now let's take it firstly for with respect to the fixed Brownian motion. Then we will get this one, and it occurs that this is equal to this one. Now, due to the precise form of our small function phi, let me recall you, here is the precise form of our small function phi. One can check that we have such an expression which can be estimated from above by this integral, which is finite. So we have density of occupation measure. Even from this calculation, one can see that on this stage, where we consider expectation of Fourier transform of mu t in square, one can add absolute value of lambda in some positive power. So one can say that even this density belongs to some fractional Sobolev space. By the way, for the same function, one can define the local times exactly at the point 0. As usual, this is a square mean limit of such an expression, where P epsilon is a standard is a Gaussian density with 0 mean and variance epsilon. Now let us consider a more interesting situation when we have two independent white noises in reproducing kernel space H phi, and suppose that all this triplet Xi1, Xi2, and Brownian motion, planar Brownian motion B are independent. Define new planar isonormal process as follows. This is eta t. And let us consider self-intersections for eta. Now, some surprising things occurs. Let us define for fixed omega the following sets. A indexed by B, our Brownian motion, is the set of pairs of moments of the time S, T, such that S is less or equal than T, but Bs from omega is equal to Bt from omega. So this is an intersection set for planar Brownian motion P. We know from Dvoretsky-Erdős-Kakutani theorem that this set is non-empty, and even rich, that we can calculate its Hausdorff dimension, so on. And define in the same way, define a eta. This is St such that eta s from omega equal to eta t from omega. Now let me recall the definition. Here is the definition of our process eta. From this definition, at least from the first look, it is evident that if we have some point, some two points S and T such beta T equal beta S, BS, then maybe eta T also will be equal eta S. This is more or less true, just we have to justify some technical detail. But it occurs that we have some extra points of self-intersection. So let me show you. This is justification which I mentioned. I consider such modification of Brownian motion, which is continuous, of course, it is usual, and I consider such modification of eta. Oh, here is mistake. It must be psi. Excuse me. Here must be not eta but psi. Let me. Here is not eta but psi 1, psi 2. As we mentioned with you, it has a continuous modification on any set phi capital, and from B0R. So I consider such omega that we have such a continuous modification. This allows us to conclude that we have the inclusion, as we discussed. So we have for such modification the inclusion. The self-intersection set for Brownian motion is contained in the self-intersection set for isonormal process eta. But what is interesting is that with positive probability, AB is strictly smaller than A eta. So we have extra self-intersection points for our process. How one can check it? Let us consider two non-intersecting subintervals, I1 and I2 from 0, 1. And consider such event f from this is subset of omega, and this is element of the sigma field, so this probability event such that the distance between the images after a Brownian motion of I1 and I2 is greater or equal than some delta 0, which is greater than 0. Then it can be checked that this limit, and here is the limit, exponent, expectation, here, double integral. This is P epsilon, which is now two-dimensional Gaussian density with 0 mean and epsilon multiply identity covariance matrix, and we multiply these things on the indicator of our event f, and it can be checked that there exists the limit, and this limit is separate from 0 and plus infinity. What does it mean? For example, suppose that we haven't intersections here, then it will mean that our that a graph of our eta on the intervals I1 and I2 are not intersecting. Then there exists some distance between them, and then when substitute this difference into P epsilon, we will get the expression which rapidly decreases to 0. So it will be 0. Yeah. So we definitely have new self-intersection points. The picture is like follows. We have self-intersection points for Brownian motion, and we have self-intersection points for eta. Now we will switch, we will discuss the self-intersection local time for process eta. And it can seems from this picture that maybe it must blow up even faster than the self-intersection local time for planar Brownian motion, because we remember that when we use usual L2 approximations with the Gaussian density for self-intersection local time for Brownian motion, then we get the expression which goes to plus infinity like a logarithm 1 over epsilon. Yeah? And it at least in my case, I explained this phenomena just a big number of these self-intersection points, like on the left picture. But you see the right picture. In this case, we have even more self-intersection points, and of course, near diagonal, the density of such points will be bigger than on the left picture. But then I understood that not only the like the size of the set of self-intersection point plays a role, but how far these points are one from another. And you see that now we measure the distance. We measure the distance between. Let me recall. Between the points eta, at least in square mean, with the help of the kernel phi small. So, if kernel phi small has a kind of let me draw phi small has a following kind, then these self-intersection points are far from one from another, because one can have, for example, like in case of Brownian motion, one can have very close. It can be a very small distance here. Oh, excuse me, not 0 but 1. But distance between two these bells is rather big because of this function phi. Of course, it goes to 0 too, but not so far, not too fast. This is a reason why we have the following statement. There exists a limit in the square mean of this P, this approximation, but I just forget the condition here, alpha, which we already discussed. What is it? Must be from this interval. This one.
Andrey Anatolyevich, so for Brownian motion, you have to subtract, but for eta, you don't have to subtract some logarithm.
Exactly. This is my point. This is a phenomena which I wanted to show you because of, as I said, we have a lot of points of self-intersection, but the distance is new. The distance between these points increases. Now we must measure the distance on the infinite dimensional sphere in this reproducing kernel space, and so due to this, we don't need to have any subtraction. So we have just usual local time of self-intersection. And actually, the calculations here are very beautiful, but I did these calculations before. Let me just recall the idea of the calculations. Let me just, I will take another pencil. Okay, maybe this one. Okay, so what we want to have. Of course, we will check the expectation. Here we have this one. We can even, I suppose, but I haven't strictly written proof, but I suppose that for any k, the k intersection local time also exists without any normalization. But for this case, so just consider this one, delta 0 from this eta t4 minus eta t3 and multiply by the same delta 0 eta t2 minus eta t1, and let us calculate it firstly when we fix trajectory of Brownian motion. Yeah? Then one can get the following. Sorry, maybe no. Let me add new pages. Okay, now we have new pages, and then we will get the following. We will get the expectation, and a double integral, which is back delta 2 multiply on delta 2, and here we will have up to the constant, and here a Gram determinant of what? It will be like phi. Excuse me. It will be like eta 1. It is related to the first coordinate, t2 minus eta 1 t1, and here is eta 1 t3 minus eta 1 eta 1 t4, for example. Okay, and here is dt. I wrote here Gram determinant related to the increments of the process eta 1. This is just one coordinate, but I have no square root, so I put here Gram determinant. It's okay. Now what happened? When we consider, now let us consider a random field eta 1, okay, no, eta 1 from U, where U belongs to our, for example, some big ball, B0R. Then what we have? This will be 4 points. This is BT1, BT2, and so on. Yeah? And then we can substitute our gram determinant estimated from below by the following. You remember our function phi small. Our function phi small is now the product of two functions. Due to this, one can draw here the square with the center of this point, maximal, which does not contain any other points, and we can just estimate our conditional variance as follows. Take a random field with respect to one coordinate, and do, for example, with respect to this one, and do estimation. Then with respect to another coordinate and do estimation. And then we have to add to this estimate. And due to the, I just say this because I already showed this at our seminar. It arises in our joint work with Olga Izumtsov and Alexander Nedin. And exactly for such function phi, which I mentioned, exponent minus u1 in power alpha, we get estimation from above from the work of Kuzik and Dupree, and it follows that one can estimate it like 1 over R1 alpha plus R2 alpha, where this R1 and R2, this is a size of our rectangle. So after this estimation, we can came back and do integration. So this is an idea, and I'm sure that at least for special alpha, it will work not only for the case when we have double self-intersection, but it will work for general case when we have multiple self-intersection. So what happened? It occurs that isonormal process reflects some properties of Brownian motion, but it improves some of them. For example, this one. And from this point of view, I think that at least it is in plans that I can consider Tube formula for this isonormal process without renormalization and with usual powers of epsilon instead of logarithm. This is my point, that I propose to you the construction of process which is related to Brownian motion, reflect its properties, but maybe it has a much more good properties due to the new distance which we introduce by using this lifting of Brownian motion to the reproducing kernel. Of course, reproducing kernel space is infinitely dimensional space, but it seems that we have not to afraid this infinite dimension. Sometimes it can help and simplify some phenomena. This all of what I wanted to say today. Thank you for attention. Maybe some questions or comments, please.
Could you please comment? Oh, I have the following question. You have just usual limit in L2 sense. Is it possible to get a measure, some measure?
Yes, you see this calculation which is related to one-dimensional case like here. These calculations also can be done in this
So
two-dimensional case.
for double intersection, yes?
Yes, for double intersection. And we will have the measure. And of course, again, as I said, it seems, but I did not write it precisely, but it seems that even in this calculation, when we put module of Fourier transform in square, we can just add norm of lambda in some small but positive power. From this point of view, one can say that we have some fractional Sobolev density.
So there are a lot of points.
Yes.
Okay, thank you. So the set of self intersection of this eta is much richer.
Yes. The self intersection points is much richer. Yeah.
And it has positive Lebesgue measure.
You see, I don't know at the moment, because it was not my aim. As I mentioned to you, I just noticed that maybe this is a right idea to use this distance in the reproducing kernel in order to have tube formula or everything like this. So when I will do this in this direction, I will answer to your question. Right now, I don't know.
Okay, thank you.
May also I ask maybe very naive question? As I understand the process eta, it is not a semi-martingale, right? Therefore, you cannot use the theory of stochastic analysis.
Yes, because you see this function phi is just positive definite continuous function. So it can be, as I draw such a bell with, let me somewhere, this bit, such a bell with which is very narrow, yeah, and then we cannot expect that eta will be a semi-martingale. This is like fractional Brownian motion. Yeah, you see, semi-martingale only for some values of Hertz parameter.
But you showed at least some example of function phi, and their function phi, at least for alpha larger than 1, it was differentiable function. So there, it has some kind of regularity.
Function phi, yes. Yes, as I said, in general, we cannot say that it is semi-martingale, but maybe, for example, when alpha is equal to 2, one can check that it is semi-martingale. But you see, as I said, it was actually, it is a good idea to consider, to apply semi-martingale technique. So when I began to study this process, of course, I just thought, oh, maybe it is semi-martingale, let us apply some calculus. But after that, I discovered that it is non-Gaussian, you see? It is it has just Gaussian one-dimensional distribution. So for Gaussian process, we can have some conditions in terms of correlation function from book of Jacot and Shiraev, when this process became to be a semi-martingale. But this is not a case. So at least at this moment, I thought that I will spend much more time just checking is it semi-martingale or not, than do something else.
May also I continue, because actually I thought that the problem is that it is not semi-martingale because of this random media. I mean the Gaussian noise on which you act, by which you act on the function phi of beta. And my question and actually idea was whether we can fix, say, this eta, and then work with the process for fixed eta, and probably then we can say something more about the local time, and after that goes to the randomness of eta.
Fixed, okay. You see, actually, yes, this is, as I said, the main idea of this investigation looks like we have some object, by the way, not only process, but also measurable process. I hope sometime I will speak about this. We will characterize it by the function in the reproducing Hilbert space, and of course study the properties of its trajectory. But you know, for description of the properties of the Hilbert valued trajectory, we haven't a lot of machinery. Just, I said, you can say that it belongs to some slim compacts. We can calculate its entropy and so on. This is a Hilbert space, infinite dimensional Hilbert space. So still we need some finite dimensional characterization. And this Xi helps us to do this. For example, as I said, main idea which we main conclusion which we can get from the last statement is the following: that we have to consider proper distance on the plane in order to get self-intersection local time for Brownian motion with good properties. This is my point.
And I have one more question.
Mm-hmm.
Your process, does it have a usual local time?
Yes, you remember.
I mean, two-dimensional process.
Two-dimensional, you know, I think yes.
Because you see, if you have a fractional Brownian motion with very, very small Hurst parameter, it has a very nice local time, which is, say, continuously differentiable n times if h is small enough. And fractional Brownian motion is pairing between generalized Gaussian process and some kernel.
Exactly.
Yes, and if this kernel are, like in your picture, are very far, then probably this helps. So
yes, exactly, and you're absolutely right. The structure of the fractional Brownian motion is more or less the same. The difference is only that in the picture of fractional Brownian motion, we have deterministic function.
Yes, you have deterministic and like stationary, just shift.
Yes. But in our case, we associate this family of kernels with planar Brownian motion, but I think that it has local time for sure.
Thank you.
Okay, if there are no other questions, then thank you for attention. And
we have to thank a speaker for a nice talk.
Thank you. And as far as I remember, next speaker will be Nikolai Ivanovich Povtenko. So see you next. Bye.
Goodbye. Have a good day.